Welcome, everyone. Let's go ahead and talk about the alternating series test for a series that has a particular form. So looking at a series that has this form where you have some alternation on the terms. So you have positive, negative, and so forth. We call that an alternating series. So for that particular series, we have a test to see if the series will converge or not. So you have to make sure of 3 conditions are satisfied. So the first condition is that your terms are all positive. So not considering the alternation, all of these terms, so u sub 1, u sub 2, u sub 3, all of these terms are positive. So we have to make sure of that. So to write this in shortcut, we can say that we want to make sure our terms, UNs, are greater than 0. Then the second condition, you want to make sure that eventually your terms are non-increasing, meaning your first term, let's say u sub n, it's going to be greater than the next term, which is u sub n plus 1. Another way you can say it is that it's decreasing. You can also think of it that way. So you can say u sub n plus 1 is less than or equal to u sub n. That's another way of considering the same statement. And the last thing you want to check is that the limit of your sequence un goes to 0. So this is considering that the limit as n goes to infinity of un approaches 0. So if 3 things are satisfied, then by the alternating series test, that particular series converges. So let's go ahead and look at some example and see how we can apply this test. So this is our first example. We want to know if this series will converge or diverge. We're going to apply the alternating series test because of this factor. It will make my terms alternate. So let's go ahead and write down a couple of terms so you're familiar with how it looks like. So when n equals 1, you have negative 1 to the 1 minus 1. You'll have 1 over 1. So it'll be 1 over 1. And when n equals 2, you have 2 minus 1 there, so that's 1. Negative 1 to the 1 power, so it'll be negative 1 over n equals 2, so that's 1/2. And then the next time when you plug in n equals 3, you'll have a positive even exponent, so there'll be positive 1 over 3. And then the negative term will come in, n equals 4, so you'll have negative 1 over 4, and so on. So you see that the terms are alternating. So we have plus, minus, and then the pattern keeps following. So this is alternating series. So let's apply the alternating series test. So the first condition, we want to make sure our sequence. So this is your sequence UN or A sub n, if you want to call it that. I think some textbook uses that. So we want to make sure our terms are greater than 0. Well, yeah, right. They're all positive. So I got 1, 1/2, 1/3, 1/4. They're positive without the alternation. So this is good. The second condition we want to make sure is that the sequence is decreasing. So you want to show that u sub n plus 1 is less than or equal to u sub n. Eventually it's decreasing. So is that true? Well, if my formula, so if I were to rewrite this series, I can write it like this. So you have the sum from 1 to infinity, negative 1 to the power n minus 1 times 1 over n. So this is your formula for un without the alternation factor. So is that sequence decreasing? So if I do 1 over n plus 1, will that be less than or equal to 1 over n? Well, yeah, right? This is good. So, or you can take the derivative and show that it's less than 0 from 1 to infinity. But I think this is clear to see that it is a decreasing sequence. And the third condition is the limit. So you take the limit as n approaches infinity of your formula un without the alternation. So this is the limit as n approaches infinity of 1 over n. And clearly we see this limit is 0. So checked. So all 3 conditions are satisfied. So we can say that by alternating series test, this sum, this alternating series, is going to converge. So this converges. All right, so here's another alternating series. So it's alternating because of this factor, and there is your formula 1 plus n over n squared u sub n. So this piece right here, this is our formula for UN. Now let's check the three conditions for alternating series. If you want, you can write out the terms, but I think we got the idea. So I'm going to go ahead and try to see if the first condition is satisfied. So the first condition was that the terms are all positive. So U's ends are positive. Are they? So when you go from 1 to infinity, is this going to be always positive? So you should see that it is, because if you plug in n equals 1, so maybe we should write out some terms so that you're familiar with this. When n equals 1, you have -1 to the second power, so that's positive 1. 1 plus 1, that's 2 over 1 squared. So you get 2 over 1. So the first term is going to be that. The second term is going to be negative. So when you plug in n equals 2, you'll have -1 to the third power, that's -1 times, and then 2 plus 1, that's 3 over 2 squared. And the next term will be positive, so it'll be n equals 3. So this would be 4 over 3 squared, and then minus, and keep going. So we have alternation, and we see the terms are keep on, they're positive. So this is positive, positive, positive. So the first condition is good, just observing that. The second condition, we want to make sure that the term UN plus 1 is less or equal to UN eventually. So now let's check that. So is that true? So UN plus 1 would be 1 plus n plus 1 over n plus 1 squared. Now is that less than or equal to UN? That's 1 plus n over n squared. So on the numerator, we get 2 plus n over n plus 1 squared. Is that less than or equal to 1 plus n over n squared? So maybe it is difficult to see, but I would go with it is true. So here you can tell that this has more terms on the denominator than this one. So clearly it's going to be less than that one. So this is also true. If you want, you can test the derivative and show that it's negative on certain interval. But I'm going to go with it's true just by observing. And the third thing I want to show is that the limit as n approaches infinity of UN goes to 0. Well, let's check. So we take the limit as n approaches infinity of 1 plus n over n squared. That's our formula. So now, since we're taking the limit as n approaches infinity, we can divide everything by the highest power of the denominator. So you'll have the limit as n approaches infinity, 1 over n squared plus n over n squared over n squared over n squared. So that's going to simplify to the limit as n approaches infinity, 1 over n squared, so that doesn't simplify. N over n squared, that will simplify to 1 over n, and on the denominator, we get 1. So if you take the limit of this as n approaches infinity, you will have 1 over n squared plus 1 over n. Both of these will go to 0. So this limit is 0. So the third condition is also checked. So what does that tell us about this alternating series? It'll converge by the alternating series test. So we can say that this series converges by the alternating series test. All right, so let's test if this series converges or diverges. So since it is an alternating series, so because of this, we know it's an alternating series. We're going to apply the alternating series test. So let's write out a few terms. So if n equals 1, we're going to have, so 1 n plus 1, so that would be 1 plus 1, 2, so it's positive 1. 1 squared, so that would be 1 over 1 cubed plus 1, that would be 2, so it's 1/2. So the first term is 1/2. The second term is -2, so it'll be 2 squared over 2 cubed plus 1. So that'll be 8 plus 1, that's 9. Plus, and then the next term is to the third power. So when n is 3, you'll have 3 squared over 3 cubed plus 1. So that would be 27 plus 1, that's 28 minus, and so on. So this is keep on alternating, and the terms are decreasing. I hope you can see that. So let's check. So the first condition, we want to make sure our terms in the sequence are all positive, and they're true, they're all positive. We have 1/2, 2 squared over 9, 3 squared over 28, and so on. So they're all positive without the alternation. Now the second condition, we want to show un plus 1 is less than or equal to un. So if you, now this might be not so obvious like the previous situations. So we want to show by computing the derivative of a function that is related to this sequence. So we can consider the following function. We can consider f of x to be x squared over x cubed plus 1. That's similar to our sequence. And we're going to show that this is decreasing on some interval from 1 to infinity. So let's see that. So consider that. So we're finding its derivative. So using the quotient rule, we're going to find the derivative of this function. So low d high, so you have x cubed plus 1 times the derivative of the top, that's 2x. And then minus high d low, so that would be x squared times derivative of the bottom, that's 3x squared, all over the bottom square. So that's x cubed plus 1 squared. Now let's simplify this and see when is this negative. So on the numerator, we can simplify 2x times x cubed, that would be 2x to the 4th, and then plus 2x minus, and then 3x squared times x squared, that would be negative 3x to the 4th. And all over, we have x cubed plus 1 to the 2nd power. So this is equal to what? So if we simplify the numerator, we get 2x, and then 2x to the 4th minus 3x to the 4th, that's just minus x to the 4th, over x cubed plus 1 squared. Factoring out an x from the numerator, we have 2 minus x cubed over x cubed plus 1 squared. So when will this be less than 0? So I want this to be less than 0. Well, if you observe, this is always positive. Now, since we're also looking at from 1 to infinity, x is always going to be positive. So the only thing we need to see is when will this be negative, because that will take everything less than 0. So we want this 2 minus x cubed to be less than 0. When will that be? So if you solve it, you will have 2 is less than x cubed, and then cube root both sides. So you have cube root of 2 is less than x. In other words, x has to be greater than cube root of 2. So let's say about 2. So when we're greater than 2, it's going to be always decreasing. So we can see that on this interval, we'll throw out the first term, and then starting from 2, we're going to have a decreasing function. So by looking at this, we can say that our sequence an, which is n squared over n cubed plus 1, is decreasing on the interval, let's say 2 to infinity. So it is decreasing on that, so that satisfies the second condition. It's also decreasing. Now the last condition we need to check is the limit. So the third condition, we want to see the limit as n approaches infinity of un. This would be the limit as n approaches infinity of n squared over n cubed plus 1. So that's the formula. And now again, we do the same thing. We divide everything by the highest power on the denominator. This is the limit as n approaches infinity, n squared over n cubed divided by n cubed over n cubed plus 1 over n cubed. So this would give you the limit as n approaches infinity of 1 over n over 1 plus 1 over n cubed. And so clearly we can see that this limit is going to be 0. So the third condition is also checked. So now we can conclude by the alternating series test, this will converge. So this series converges. All right, here's the last problem for today, where we want to see if this series converge or diverge. So it is an alternating series because of this factor. But if you try to consider the last condition, which is to take the limit of your un. So this is our un. So I'm going to rewrite it this way. So this is the sum from n equals 1 to infinity, negative 1 to the n times 3n over 4n minus 1. So this piece right here, this is our formula un, the sequence. It's alternating, so I can see that if you do the alternating series test, the third condition, you take the limit as n approaches infinity of your un, which is 3n over 4n minus 1. And this limit is going to be 3 over 4, which is not 0. So the alternating series test doesn't work for this particular series. So the alternating series test fails, which means we have to use another test. Now, we have talked about the nth term divergence test. That's what we're going to apply here. So if you do the nth term divergence test, which told us to just take the limit of our sequence. So you take the limit as n goes to infinity of negative 1 to the n times 3n over 4n minus 1. This limit does not exist. So therefore, by the nth term divergence test, this diverges.